So this morning what I'm going to talk about is how to define big data. It's something we've been working on at IDC for almost 2 years now. Why people are interested in it, and I've talked to a number of groups recently with standing room only, which is just amazing. Makes you feel like a rock star, even if your mother doesn't know what you're talking about. What the technologies are behind it, specifically text analytics and big data and how they fit together, and then what hotspots we see in the marketplace. So I have 45 minutes, and I hope to leave some time for questions and answers. Let's see if I can. Also, I will be around for the next 2 days, so if you've got questions, make sure that you find me, and I will be here and try to answer them or send you to the appropriate person at IDC. So this is by way of background. The digital universe. This is a study that we do every year. The content is always different, depends on who's the main author. But in general, we try to size that digital universe, look at the hardware, the software, trends, etc. You can find it because they publish it and support it on the EMC site. And I did give you a URL. I'm not going to read it out because it would take too long, but please either check the video or I'd be happy to send you the URL. It's full of useful information. The whole point of it is in 2009, we had 0.8 of a zettabyte. A zettabyte is 1 trillion gigabytes, and I can't even imagine how big that is. It's very large. And by 2020, there will be 35 zettabytes. This means that you can't afford anymore to hire every English major in the world in order to tag your stuff. What are you going to do? It requires an entirely different approach to finding information. The other thing that you need to know about that very large 35 zettabytes is that not all of it is particularly valuable. A lot of it is transitory, but you never know what's going to be valuable, witness tweets, until you are looking for that kind of information. And being able to sort the good stuff and the valuable stuff from the mountain of garbage is another very important factor that we're not talking about an awful lot. So what we find in this market is that we've got a set of technologies that can do a lot of terrific things, and the combination of those technologies that's suitable for your application depends greatly on what it is that you want to do with what kind of information, how fast it is arriving, how long you want to keep it for, and what else you want to combine your text with. So there are a lot of it depends in this world. It's not a matter of creating a single schema for a single relational database or even 100 relational databases. Rather, we are into the big leagues now as far as information is concerned. All right, what is big data? It is a new set of technologies and a not so new set of technologies that we use in combination to solve very complex problems economically. In other words, it gets deployed on pretty much commodity hardware. And that means that people who didn't have supercomputers are able to do things that they didn't used to be able to do. So what they do is they collect and manage and mine and analyze large volumes and streams of varied information from multiple sources, and use that analysis to either predict what's going to happen or to manage their decision making. I will show you a number of examples. What we see is that the organizations that are already adopting these technologies have such a competitive edge that they refuse to allow us to talk about them in public for the most part. And that tells you something. In other words, they get a faster understanding of customers, of products, of patients, of trends, of the weather, if you want. If you remember nothing else, remember this bell-shaped curve from my talk, because I think that this represents the fundamental difference between big data and business as usual. When my grandfather started his business a long time ago, he knew every single one of his customers. He knew how to shape the services that he provided so that each individual got what he needed. When we moved into the 50s and 60s and 70s and 80s, and we had larger customer bases and trained managers, what they were trained to do was to look at the center of this bell-shaped curve over here. And they geared all of the services and products to the center of that bell-shaped curve. What that meant was that either end of the curve, which has substantial customers or patients or data underneath it, depending on what you're looking at, was ignored. It was one-size-fits-all business. When you have a lot of data, you can afford to micro-segment that curve. In fact, what you've got is a series of bell-shaped curves, and you can start to address the long tail on both sides of the center. If you do that, you change healthcare because you're looking at diagnoses for people of a particular genetic makeup, a particular demographic, with a particular set of problems, some of which may be related and some of which won't be. You look at customers who want a subset of what you may provide, but you're not providing it. And yet, even 10% of 1 million is, or 5 million or 10 million is a lot of customers, and 30% is even more. So this starts to shape your whole strategy, and it also delivers the products and services the way my grandfather thought about business. It's individualized business, it's individualized healthcare, it's individualized government. That is a profound change, and this is why organizations that have already adopted this approach are not talking about it publicly, because they have a jump on their competitors. They're developing products to serve both ends of that curve. That is a profound change. So what's going on today? We have too much information, and yet those who use the too much information aren't thinking about information overload anymore. That's yesterday's problem. They're thinking about turning it to their advantage. There's a new understanding of how to use that information. The complexity that is baffling IT departments and line of business people today because of too many sources, too many applications, and all of the complexities of compliance, et cetera, are making it very difficult to manage the information environment with traditional tools. We're seeing a synergy of information and technology, and of course the best example of that is the iPhone, the iPod, the iEverything, the iPad, because the technology delivers the content enhances the technology. So you're seeing a lot of very forward-looking hardware and software people thinking about content and technology as a single product. And then there's a market demand, and we certainly have data on this at IDC, to unite all information into a single access point. in order to increase revenue by understanding what's going on, to reduce their risk. And CFOs are notoriously risk averse, so they're starting to invest in anything that might keep them out of jail. And to improve customer relations. And then, of course, there are new technologies like Hadoop. So here are some other factors. These new technologies, cloud, the big data, NoSQL, Hadoop, et cetera. New scalable hybrid architectures that combine and are well integrated, and this is very important, the features of search, of business intelligence, of text analytics, of business analytics, of visualization, of question understanding. And this is changing how we think about what we want to do with information within the organization. Then the need for real-time or near real-time access and updating is changing how IT has to react, and the relational database just doesn't keep up with the demand. The machine learning that enables pattern discovery and this new change of attitude in which looking for trends means you don't have to have everything right. What you need to do is to be able to understand a body of data as it flows in and see what the major categories are, trends are, relationships. That's different too, and the marketplace is only beginning to wake up to this. So we get a lot of people coming to us and saying, yeah, but if we do sentiment extraction, you know, we've looked at 500,000 documents, and this one over here was categorized wrong. And therefore, we're going to do it manually. Well, you can't anymore. Good luck. And in fact, consistency turns out to be one of the advantages of machine learning. Of course, consistency is also a problem for computers because they're really bad at irony, for instance, or sarcasm. But on the other hand, what most people don't know is that, in fact, human categorizers, human indexers, are really bad at being consistent also. And there are studies showing that from one day to the next, they are no more than 55% consistent with themselves. It's just that they don't make stupid computer mistakes. They make stupid people mistakes, or not so stupid. And then the linguistic technologies are now robust enough. Those of us who have been looking at these since the dark ages of linguistics are finally relieved that somebody else is noticing. And what they're doing is enabling better interaction, better analysis across sources. And that's important as you start to meld all of these sources. How do you find the commonalities if the terminology is different, the schemas are different, and how can you do it quickly enough in the big data environment? Here are two examples of what I mean by information synergy. The first one, and my poster child, is Watson. When Watson won Jeopardy, I went around grinning at all of the BI guys who kept saying, but there has to be a database in there somewhere. No, there's no database. There has to be a database. No, there isn't. You know, these were search and text analytics technologies taken to the nth degree. In fact, they had over 400 of them, well integrated. So I was feeling vindicated. I hope you are too. Multiple data types, multiple sources, hundreds of technologies. And in healthcare, and this is interesting, so, you know, they won Jeopardy. Now what do? So they spent a while, you know, considering, what do? We spent, you know, 5-10 years developing this platform. Looks like a really good thing. They went after healthcare, and it's in proof of concept right now. The example that I like is for congestive heart failure, which is the proof of concept. what they did was to take the patient records, all of PubMed, which is National Library of Medicine, online publications, genetic information, individual patient records. They aggregated the whole thing and started looking across it to see what they could do with it. They were devising a sort of a physician's assistant application. What they found, first of all, is using machine learning, they were able to discover 4 markers of, oh, and I should tell you, this is an insurance company. What they wanted to do was to keep people with congestive heart failure from being readmitted to the hospital, for which they were not going to get paid if it was less than 90 days. So there was a real, you know, this was not pure research for the good of mankind. This was how in the world are we going to save money, which is always the best way to sell software. Anyway, what they found was 4 markers that would indicate a readmission of congestive heart failure that they didn't even know about, because they were looking at patterns without the physician's biases or prejudgments about what was important and what wasn't. And some of them turned out to be pretty simple. So that's a remarkable thing. But they also found that clinicians who hate to fill out all of those health codes were able to use the text analytics aspect of this in order to fill in the codes automatically. And at that point, the physicians who were feeling a little bit threatened by having a machine prejudge what the best diagnosis would be, wholeheartedly started using it because it saved them time. The other thing is that physicians typically only spend about 5 hours a month being able to read all of that new research. So having a Watson look through it, find out what was pertinent, saved them, and kept them up to date in a way that they just physically couldn't do by themselves. Great example of big data for healthcare. The other one is an e-commerce customer service application in which you look at data, the personal profiles of the individual looking for something. You look at the click stream, the product data, the sales data, bring it all together, and then micro-segment it, as I said, so that you can offer targeted suggestions to an individual with a particular profile who has asked a specific query, and you do it in real time. So big e-commerce sites are all over this. This is why Amazon is investing so heavily in this area. All right, let's dive into the technologies. This is what's going on. The red that you see are software technologies. The blue are hardware. Supercomputing is both, of course. That's why it's 2 colors. And on the bottom, you see some horizontal applications. All of these are circling around big data. There's a lot of noise that they're all making. Some of them are really big data. Some of them are not really big data. Let's talk about that. So the building blocks that we saw, and this was a group of analysts coming from software, hardware, services, telecom, et cetera. And what analysts like to do is talk a lot, and we also argue with each other. So it did take us about a year to come up with something we could agree on. So first of all, layers of the big data infrastructure or platform, if you will. First of all, the infrastructure, the hardware. I put it in gray because I don't look at it, of course. The data organization and management, very important in text analytics and search. So that's the input. The analytics and discovery that we put on top of the collection once it has been organized. And then, even more important for users, the interface and the applications that are built on top of the bottom three. And I'm calling those info apps. So, I mean, one of the things you can do as an analyst is name things, right? And I did name search-based applications and then decided it was pretty boring. So that's why I'm calling them info apps. So, as I said, a new generation of technologies and architectures to economically extract value from large volumes of data in collections or streamed, high velocity of streaming data. And those two things are different, remember, in terms of the technologies used to analyze a collection versus the technologies used to analyze a stream. A variety of formats, structured, unstructured, images, CAD/CAM, etc. These technologies capture, store, monitor, analyze, and discover trends and patterns in either batch mode or in real time. This is another one of those, it depends on how you're using it and what kinds of information and how fast it's arriving. What we're seeing is that the greatest value is derived from the most complex combination of sources and technologies. So the way we're defining this, and this is this year's starter definition, is that either you have to have 100 terabytes collected, or more, of course, or the data is received through ultra-high streaming, or the data generated is growing at more than 60% a year. And this is a little wishy-washy right here. We will tighten it up as we get more experience. It must be deployed on scalable commodity infrastructure, not a supercomputer. And it has to have either 2 or more data formats and sources, or it has to be high-speed streaming data. And that gives you the volume, the variety, the value, and the velocity, the 4 V's that everybody is starting to talk about in relation to big data. Now let's look specifically at the part of the big data world that I am concerned with. Each of those lozenges is a different use. Along the vertical axis, what you have is increasing complexity of technologies and number of sources. Actually, what I needed was a sort of a 6-sided something or other, but we've had to flatten it for PowerPoint. And time along the bottom. So let's look at this. If you just have a few of those technologies, like categorization, like clustering, like search, for instance, you can do log analysis, ad targeting, smarter planet stuff. In other words, you've got a stream of data coming in, sensor data, for instance, or churn detection. If you want to do relationship detection, specifically in the text analytics world, you need much deeper parsing to find out what the relationships are among entities. And then you have to add predictive analytics if you get into fraud detection, decision support, climate modeling, certainly, government intelligence applications, and things like IBM Watson that are coming on the market today. Investment trend detection. So each one of these takes, those hundreds of different technologies or flavors of those technologies and uses them differently within specific domains. And that's important too, because as we get into language, of course you know that the specific domain makes a difference because we use words differently. Bank of a stream versus financial institution. So we need to disambiguate all of those words, and that's why the domain knowledge is so important if you want to get to a higher degree of accuracy. So what are the challenges? First of all, they're complex. The problems that are the most valuable to solve are the ones that you can't solve with, out-of-the-box technologies today. the fact that the data is so heterogeneous, you've got unstructured and structured information, you've got multiple schemas, you've got multiple terminologies, the sources are internal, they're external, they have different security on top of them. That's also important. The content, especially in the text world, is very unpredictable. There's no apparent schema or structure to it. And there are multiple, this is a people problem, but it's always the most insurmountable, we find. There are multiple data owners. They have certain opinions about how their data should be or should not be used. And there's no central governance, especially when you add the external stuff. So we get a lot of questions about security in the cloud, for instance. There was one manufacturer who wanted to know, well, if they were developing stuff, could they use a SaaS application for cross-language translation? Because would that leave them open to somebody else figuring out what they were working on? And those are hard problems. Obviously, high volumes, real-time or near real-time collection, analysis and access is often needed. The users are different. They may or may not be highly trained analysts, and I can see somebody nodding his head here. That means that you have to deliver the data, not in an SPSS spreadsheet, but in something on top of that, so that they understand and can use it quickly without training. They want quick access to dynamic sets of information. They don't want to wait 3 months for a new cube to be created for them. And finally, expertise is in very short supply. Not just for things like Hadoop, but it's really hard to find a computational linguist these days who's on the market. So let's now look specifically at text analytics. I think most of you know what it is, but I just want to tell you what I'm talking about. It extracts building blocks of meaning from text. And not all applications do all of this. And whether you need all of this done, again, depends on the usage. So, syntax and grammar. You can't do relationships without them. You know, Fred hit Bill being different from Bill hit Fred. Same words, different relationships. And one you'd rather be Fred and the other you'd rather be Bill. But you don't always need the relationships. Extracting concepts, really important, especially as you go across sources because they're going to describe those concepts differently. Entities, names of people, places, and things. Sentiment, whether something or not is positive, and how do you tie it to the entity? That's one of the things that Lexalytics did very early, was to resolve the name of the product and tie it to what the opinion was. So if you've got Consumer Reports talking about lots of cars, and one of them is the Acura and one is the Kia, you don't want to tie the sentiment to the wrong car. Time, so that you can do trending. Geography, so that you can do trending and sentiment by region. Then it also finds patterns, really important. Similarity matching is one of the things that both search and text analytics brings to this toolbox of information access and management software. Because before that, what we had was exact match. What we need to know is what are the closest matches, and should they be grouped together or not. Relationships, acquisitions, collusion, fraud, similar molecules, so that if a drug is going off patent, you can find a similar one. There's your similarity matching in a very non-traditional setting. Cause and effect and trends. What we see is that deep text analytics requires a pipeline. It may not require all of these engines, But usually what happens is that you march the documents through a pipeline or parallel pipelines with the same engines or annotators on them. So tokenization, entity extraction, facets, time, event, languages. You can keep on adding annotators to it. However, one of the difficult problems is what order to put those annotators in, and how do you parallelize it? Very difficult. So what's the relationship of text analytics and search to big data? As I've said, more data improves the accuracy of hypotheses and predictions and categorization, but it has to be analyzed effectively and quickly across sources. So I call this ETL for text because database people understand what ETL is. Essentially, it's data preparation. And you can use it across multiple sources, both text and data. It's highly scalable, it's quick, it gives you ad hoc access, and no schemas are necessary, although the structure of the text is certainly very important, as I've said. Machine learning being used on any of these more advanced applications with a lot of data, because you want a feedback loop. In fact, what the Watson guys told me was that it wasn't until they added a layer of machine learning on top of what they were already doing that Watson became championship material instead of just sort of humdrum average contestant. So detecting changes and anomalies, finding patterns across data stores, all of these things you find text analytics and search being very useful for. The fact that it's consistent, as I've said, and it tends to improve the performance of these complex systems at multiple levels. Let's take a look at what those are. So this is very conceptualized. On the bottom, you've got the data sources, the content sources. Then you've got something which has turned into an actual business, smart connectors and schemas, XML tag data. Lots going on with those connectors now. And we need more and more connectors as we have more and more sources. On top of that, the information infrastructure with, the BI, the search, et cetera. The databases, certainly. Knowledge bases that, for instance, taxonomies and ontologies, lists of terms, list of products. Very important. It's not that you can't do good text analytics out of the box. It's sure better than nothing. But in order to get above, say, 50, 55% accuracy, which is fine for some applications, you need to start adding in that domain knowledge. Then the access and analysis, that's your BI, that's your analytics of various kinds, your visualization, your reporting tools, and then those two blue layers at the top, the interface to all of the stuff below, and the applications, the information applications that you build on top of this so that those inexperienced line of business users can have a very easy-to-use work environment with access to a fairly complex underpinning or foundation without having to figure out which application to use and how to use it. That's going to be a profound change in the IT industry, but that's another talk. So where does text analytics come in here? First of all, at the bottom, for data prep. And as I said, I call this ETL for content, but actually it works for content and data if there's text in the data. So normalizing across all those sources, extracting the entities, the time, the sentiment, et cetera, tagging that information as it goes into the collection, and parsing it for the syntax and grammar. Then at the access and analysis level, the relationships, the cause and effect, and the trends are analyzed using text analytics. So essentially, you've got the same pipeline doing multiple things. And finally, and this again is to go back to Watson, a new area that they were very, very good at, and you're going to see a lot more of it. That's question analysis, bilinguistic analysis type, lexical analysis type. So this is a question that needs a geographic answer. This is a question that needs a product answer, et cetera, et cetera. We have never spent enough time understanding questions, and therefore we have been returning great answers to the wrong question. So you're going to see a lot of research in this area, a lot of new designs in order to make those applications useful. So here are hot areas for web search, for big data. We see it, in fact, a lot of it, like Hadoop, came out of web search. Healthcare, early product warning. There are auto companies, auto manufacturers that have been using early product warning, so far as I know, back to about 2001, very quietly, to find out when they have a problem with one of their products, and then trying to defuse the situation before it literally blows up like the Ford Explorer. Churn prevention. SPSS has been doing that for a long time. They grab the phrases that are indicators of a customer, and a telecom customer about to jump to a new service, and they offer a better package based on that in order to keep the customer. I happen to know some of those phrases. I can tell you that it works like a charm. So I wanted to give you some examples. Here's DataSift. And if you look at these Twitter examples here, you will see that, and this goes on for about 2 miles, but I couldn't fit it all on here. These are fields that they can extract from a simple tweet. And in fact, here's a map of a tweet. And you can see that they're not just looking at the text, they're looking at all the information that you get around the text. Who is this person? What's the date? Who's the author? The idea of a tweet, the retweets around it, the author's screen name, the author's username, the author's location. As I said, it goes on and on forever. And it's really amazing when you consider that they're getting this out of 140 characters. And here are some of the fields. So this is the data prep part of using text analytics. And, you know, one of the dirty little secrets about text analytics and content analytics is that the more prep you do, the better the results. There's just no way around it. So reputation management, this is a great one. This was about Whirlpool. What they did was start to analyze all of the social media, Twitter, Facebook, traditional media as well, for opinions about their products. They set up a unit called Digital Detectives. And the digital detectives go after, well, that's a nasty way of thinking about it. They contact the people who are posting complaints about a particular product and proactively try to help them solve a problem with their washing machine or whatever. And that's the first thing. The second thing is they are tracking sentiment over time, and they're also grabbing product suggestions. You know, hey, how come you don't make pink washing machines? I think that would be great, you know, et cetera, et cetera. So several uses of the same data to different depths, because trending doesn't require the individual level. It just requires the trending, the surface kinds of text analytics. Here's a Lexalytics example. You've got, for CRM, you've got a list of customers along the left-hand side, and then you can see by customer the sentiment that they have found relating to each one of those. Very important as you start to develop these info apps that you think about the visualization aspect of it, because I understand a lot more this way on the right than I do on the left, but it's the same data. Same thing over here, you got negative, positive, and neutral sentiment over time, and you can dig down by clicking on any of these in order to find out how come the negative sentiment leaped between March and April. What was going on? Was there a product release? What happened? Was there something in the news, etc.? So again, what's going on? Thank goodness most of it's neutral, and that there's very little of it that's negative, which is the red. Here are a couple of other examples, and I'm almost at the end here. This was a financial services firm, wanted to monitor trading data, and in investment in banking and stock trading, being able to be even 30 seconds ahead of your competitors means a difference in the stock price. So they wanted to grab the trading data, establish rules for each portfolio that would trigger buy or sell orders depending on that portfolio. And their problem was that the trade data exceeded their relational database capacity and also speed. So they used the big data techniques in order to process the trade data in real time, and it increased the trading responsiveness by several orders of magnitude, and no, I can't tell you who it is. Fraud analysis. U.S. government using the same technologies to detect patterns of fraud in healthcare programs. Again, lots of data. Could they detect patterns rather than looking at each individual, and then develop alerting so that if somebody was following this pattern, they could take a closer look at them? It's a way of cutting the data down to a manageable size. And they boosted recovery of claims from $1 billion a year to $50 billion a year. Not bad. Your taxes at work. Here's your taxes at work again. I can tell you about the problem. I can't tell you about the solution, or they'll kill me. This is the Government Intelligence Agency. They wanted to detect threats and understand relationships among people across and around the world in many languages and organizations. And they needed to discover those relationships, detect changes, sift out important data, and above all, failure was not an option. So important stuff. And I was with an analyst who was looking across sources and discovered a relationship between a criminal organization and a terrorist organization in terms of funding that they didn't know. And this was just a demo. So it works. So in summary, the information explosion demands new approaches to managing, to finding, to analyzing information across all sources. Big data applications, and this is important, are disruptive. They're disruptive to the IT industry, to business, to healthcare, to publishing, to science and research. And that means that those who are adopting it need to be on the alert and to start developing these applications sooner rather than later. It enables big data organizations to organize, to monitor and analyze the state of their business quickly. Discovery is a key element of patterns and trends and relationships among all of the objects and people and events in the database. And the most valuable applications, as I've said, merge multiple sources of information of all types and use multiple technologies for analysis, alerting, and prediction. And finally, here's my poster child, because what happened with Jeopardy was not that it was just fun, but that it created awareness that all of us who have been in this industry for many, many years were unable to do by ourselves. So thank you very much. While the next person's coming up, if you have a question, I think I can take it. Is that all right? Anybody? Too much information, huh? There's one back there.
Hi there. I just wanted to ask a question. There was one of the slides where you referenced that you want at least, I think it was 100 terabytes of data or something.
Why?
Actually my question is, as we see the rise of more data, what are cases that you can talk about where there's too much data and you need some sort of filtering to get to the data that you're really interested in, and how do you see that becoming more important as we get more data?
That's a great question, and that's one way that a lot of use cases we see are using Hadoop. So they'll use Hadoop, which is batch, as a way of cutting that information down to a much more manageable size before they look at the sub group of information about a particular topic. So Hadoop is like an initial, it depends, it can cut it down, or the other thing it can do is define clusters of information without your having to specify what the categories are ahead of time. And the whole point of this, I mean, obviously I can talk for days about it, but what you're looking for here is not what you expected, but what you didn't expect. This is all about discovering surprises. That's what makes it so valuable. And using Hadoop as that first cut appears to be an emerging best practice for voluminous amounts of information. And then using the other tools, which are sometimes more traditional. In fact, it can get down to the spreadsheet eventually, which is, the analyst's preferred tool these days. That help? Okay. Other questions? Yes.
Where's the line between data analysis and where's the line between going through all of this data and privacy?
Great one. We don't know. It's, one of the major issues is privacy. Now, within the organization in the United States, the organization essentially owns what you do on your computer or on your telephone. So that's a little easier. Then if you move to Europe, that's not the case. If you move to the web, there's this whole question of opt-in versus opt-out, implicit search, recommendation engines, how much are they invading privacy? What I see is several approaches. So within the organization, regular security can apply, right? Outside of the organization, you can have explicit opt-in, opt-out. You can also aggregate data and anonymize it so that what you're looking at is the aggregated microsegment, if you will, without names attached to it, and use that against the query to return a recommendation without looking at the user's profile. And that still gets you a better answer. Other questions? I will be around, so if you think of other questions, please ask. Thanks.